Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over how to calculate the activation energy of a catalyzed reaction when we're given information about the uncatalyzed reaction. And so let's get into this. Okay, so we're given that the activation energy of a certain uncatalyzed biochemical reaction is 50.0 kilojoules per mole. In the presence of a catalyst at 37.0 degrees Celsius, the rate constant for the reaction increases by a factor of 2.50 times 10 to the third as compared with the uncatalyzed reaction. Assuming the frequency factor A is the same for both the catalyzed and the uncatalyzed reactions, calculate the activation energy of the catalyzed reaction. Okay, so they gave us a bit of information here. They told us that in the presence of the catalyst at 37 degrees Celsius, the rate constant for the reaction, the catalyzed reaction, has increased by a factor of 2.5 times 10 to the third as compared to the uncatalyzed reaction. So we could write that as an equation. So we're focused on the reaction constant or the rate constant, right? So that means that the rate constant for the catalyzed reaction, right? And so we'll put C for catalyzed is going to be equal to the rate constant of the uncatalyzed reaction. We'll put UC for uncatalyzed, multiplied by 2.50 times 10 to the third. So this tells us, right, this is the equation or the equation, how should I say, representation of what we were told, right? So we're told that in the presence of the catalyst at 37 degrees Celsius, the rate constant for the reaction, the catalyzed reaction, has increased by a factor of 2,500. So the rate constant K is equal to the rate constant of the uncatalyzed. So K, the rate constant of the catalyzed reaction, is equal to the rate constant of the uncatalyzed reaction multiplied by 2,500 or 2.50 times 10 to the third. So now that we have this, let's write out what the Arrhenius equation is for both of these, right? So keep in mind that for K, the rate constant for the catalyzed reaction, again, that's going to be equal to A, the frequency factor, multiplied by E raised to the power of the negative activation energy. And again, we're going to specify or distinguish this as the catalyzed activation energy, so we'll put a C there, divided by the rate constant times the temperature. Now, with regard to temperature, well, here, I'll get to temperature in just a moment. Let's go ahead and write the same expression for the uncatalyzed reaction. So K UC for uncatalyzed is equal to A times E, again, raised to the activation energy of the uncatalyzed divided by RT. Okay, now we can plug these into our equation here. So let's go ahead and do that. So for Kc, we'll substitute this. So here we have AE raised to the power of the activation energy of the catalyzed divided by RT equal to, and now we have KUC here. We'll replace that with this here. So that's going to be equal to, again, that's going to be A times E raised to the power of the activation energy of the uncatalyzed reaction divided by RT. And then again, this is going to be multiplied by the factor 2.50 times 10 to the third. Okay, so now that we have this equation in terms of the frequency factor and activation energy time and all that, now we can kind of simplify this equation and we can drop some stuff. So the first thing is, again, we're told to assume, where are we close those? Assuming that the frequency factor A is the same for both reactions. So we'll notice that these can cancel out if I divide by A on both sides, right? A will cancel out because they are the same. And so then I'll have E raised to the power EA, the activation energy of the catalyzed reaction over RT, equal to E raised to the power of the activation energy of the uncatalyzed reaction, again divided by RT. And again, this is multiplied by 2.50 times 10 to the third. Now, we can simplify this. We can get this on this side. So let's go ahead and divide both sides. So we're going to divide both sides by E to the negative activation energy of the uncatalyzed reaction over RT. And we'll divide this by the same. So this is E raised to the power E, a activation energy of the uncatalyzed reaction divided by RT. Okay, so this cancels out. And then I end up with this equal to this, right? So do I have enough room? Yes, I think I do. So here, then we'll have E raised to the power of negative EA catalyzed over RT over E to the power of the negative activation energy of the uncatalyzed, again, over RT, and that's equal to 2.50 times 10 to the third. Okay, so now we have this here. Let me put a box around it so it's clear what we have now. Okay, so now we can continue to simplify this, but we're going to have to use the laws of the natural logs. Okay, so now that I have this, I'm going to erase this because we don't need that anymore. We'll continue with this. Now I can take the natural log of this side, but then if I take the natural log of this side, I have to take the natural log of this side. So now what I end up with is I'm going to take the natural log of this ratio, this fraction here. So it's going to be E raised to the negative activation energy of the catalyzed reaction over RT divided by E raised to the negative activation energy of the uncatalyzed reaction over RT. So I'm taking the natural log of this side, and then I got to take the natural log of this side. So that's going to be equal to the natural log of 2.50 times 10 to the third. And when I calculate this out, right, the natural log of this becomes, what did I calculate? 7.8240. 7.8240. Okay. So now I have to remember my laws for natural logs. And they're pretty much the same as the base 10 base 10 log rules or laws. If I take the natural log of two things divided by each other, then it's the natural log of the top minus the natural log of the bottom. So let's rewrite that. So that becomes the natural log of the top. So the natural log of E raised to the power of the activation energy of the catalyzed reaction over RT minus the natural log of E raised to the power here. So negative EA of the uncatalyzed reaction over RT. Okay, so now I have in that form, and then that's going to be equal to 7.8240. Okay, so far so good. Now I can simplify this. So again, one of the rules or laws of natural logs is that the natural log will undo e. So if I take the natural log of e raised to some power, the power becomes the term itself. So these kind of cancel each other out. Just like if I had a square, right? So if I have x squared, and if I take the square root of x squared, the square root and the square will cancel each other out, and I get x left over. Same thing with natural log and e. If I have natural log and I take the natural log of e and it raised to some power, the power becomes the term. So these cancel out. So then these cancel out, and I get just the exponent becomes the term itself. So negative EA of the catalyzed reaction over RT minus negative, so these are going to cancel out, and minus and negative, minus a negative, but minus and negative is a positive, so we'll just call that positive right away. And so it's going to be EA of the uncatalyzed reaction over RT, and again that's going to be equal to 7.8240. Okay, so we're well on our way. I know this is taking a little bit of time, but this is the way to solve the problem. It might not be the only way. It might be slightly different ways, but this is the way that I'm showing. If you have a different way or an easier way or a quicker way, put that down below in the comment section, please. Okay. Now, I have this and this. Now, notice that the R and the T are constant. They didn't tell us anything about a change in temperature, so we can assume that the temperature hasn't changed, right? So the temperature is going to be the same. R is going to be the same, so we can plug those in. We could actually take it out, actually. So we can put in 1 over RT, take that out, and then we're going to have negative, or we're going to have, we could switch this around, right? So we can have, instead of negative on this side, we can take this and switch these terms around, right? So we can do EA of the uncatalyzed minus the EA of the catalyzed, the activation energy of the catalyzed, right? And then that's going to be equal to 7.8240. Now what we can do is, since we are dividing by RT, we can multiply this side by RT and then multiply this side by RT, right? That would give us this on this side. So if we multiply, right, RT over 1, and then we multiply this by RT, right? So RT over here will cancel out, and then we'll have the activation energy of the uncatalyzed reaction minus the activation energy of the catalyzed reaction is going to be equal to 7.8240 times RT. But what's RT? R is 8.314 kilojoules per mole, right? So if we look that up, yep, 8.314. So then this is going to be, excuse me, this is going to be equal to 7.8240 times R, which is 8.314 kilojoules per mole Kelvin, multiplied by the temperature, which we're told is 37.0 degrees Celsius. We need to convert that to Kelvin. So the temperature is going to be equal to 37.0 degrees Celsius. We're going to add 273.15 to that to convert to Kelvin. And so we get 310.15 Kelvin for the temperature. So that's what we're going to multiply here by. So that's our temperature. So we're going to go ahead and multiply this by 310.15 110.15 Kelvin. Notice that the Kelvin is going to cancel out now. So now we have kilojoules per mole, which is going to be related to, again, the expected units for activation energy, which is what we're trying to find. So notice it's all working out as far as units are concerned, right? So now we can continue. I'm going to erase up here to give myself some more room again. We don't need this anymore since we've used it. So let's get rid of this. So now I have here the activation energy of the uncatalyzed reaction minus the activation energy of the catalyzed is equal to this. So all I have to do is multiply this times this times this, and I get, what do I get? 20,174. 20,000. Oops, actually not. That's actually in joules. Sorry, my bad. This is in joules, so this is going to end up in joules. So this is 20,000, what did I say? 20,174.8655. And that's joules per mole. And as I said before, for kilojoules per, for activation energy, that's usually measured in, that's going to be kilojoules per mole. So what we're going to need to do is convert this to kilojoules, right? And the conversion factor, just to be, clear, if you're not sure how to do conversion factors, let me show you, right? So I know that I have 174.8655. That's joules per mole. So I am going to put joules on top and 1 mole on the bottom. I want to convert joules to kilojoules. I know that 1 kilojoule is 1,000 joules, so I can set up the ratio here. So 1,000 joules on the bottom, 1 kilojoule on top. Joules cancels out. Now I divide by 1,000 and I end up getting 20.17 kilojoules per mole. Now I can rewrite this. So I have the activation energy of the uncatalyzed minus the activation energy of the catalyzed reaction is equal to 20.17 kilojoules. Oops, let me write this better. Kilojoules per mole. Now I can plug in the other information. So I was told that the uncatalyzed biochemical reaction, the activation energy of that one is 50.0 kilojoules per mole, right? So I'm going to put that in here, right? So that's going to be 50.0 kilojoules per mole. Let me write that better. Per mole minus the activation energy of the catalyzed reaction, which is what we're being asked, right? So we're asked, assuming the frequency, calculate the activation energy for the catalyzed reaction. So that's what we have here, and that's going to be equal to 20.17 kilojoules per mole. And let's go ahead and erase this to give us our room for the final step. So now I have this equation. So now all I need to do is manipulate the equation. So what's going to happen is that I'm going to end up with the activation energy. I subtract this from both sides. I subtract this from both sides. So I'm going to end up with the activation energy of the catalyzed reaction is then equal to 50.0 kilojoules per mole minus 20.17 kilojoules per mole. And then I just do that calculation and I get 29.8 29.8, was it 3 kilojoules per mole for the catalyzed reaction. And now this makes sense because when you add a catalyst, one of the things that the catalyst does, or the main thing that a catalyst does, is that it lowers the activation energy. So you would expect that the activation energy for a catalyzed reaction would be lower than that of the uncatalyzed reaction, and that is what you get here. Because the catalyzed reaction was 50 kilojoules per mole, therefore notice that the catalyzed reaction is less than that, 29.83 kilojoules per mole, or 29.8 if you want to round to the proper numbers. Sig figs, that is it, ladies and gentlemen. I hope that was helpful. If this was helpful, if this helped you in any way, if you enjoyed the video, then please, by all means, like the video, share the video, hit that like button. Also, help me out, subscribe to my channel. I would be great. I would be greatly happy if you did that. Also, make sure that you click the notification bell, and when you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a comment or a problem that you need help with, or if you have a topic you would like me to cover, put that down below. I would be happy to do that for you. Thanks for joining me, and have a great day.